Hello, I am Alberto Toffaili and I will present a rare and fascinating atmospheric phenomenon, jumping sundogs, also known as crown flashes. We will show how combining video analysis, ferrofluid experiments, and dynamical system modeling to explain their origin. So we are presenting a statistical mechanics model of the crown flashes phenomenon. What are jumping sundogs? Look at these images. Unlike a static sundog like this, the jumping sundog moves rapidly, resembles a luminous feather resting on the cloud, and can last up to 2 minutes. Clearly, something far from the thermodynamic equilibrium. Our central question: what are jumping sundogs and how to generate them? These are image of a video of a jumping sundog. This is the position of the sun, and here is the sundog. You see, looks like a lightsaber in the space. And these images were obtained by two bikers in the middle of the US. These images are very difficult to predict. This phenomenon is very difficult to predict why it's happening, and it's very difficult to have to position a camera to obtain this image. So we obtain this image from the YouTube, from viewers, from people in recording this phenomenon at the YouTube. And here you have the sundog, and in this part you have a regular sundog. Another image, I guess that this is from the Philippines, and you have here the 22-degree halo, and you have here the jumping sundogs. It has a shape of a plume, of a feather supported by a cloud, and you have these rapid changes in their shape. This is the main idea, the main thing that we observe in the sundogs. This sundog here was recorded close to the city of the Moscow in Russia, and the sun is at this part, and this is the plume. This is the sundog, and it will move erectly. Basically is the same phenomenon. Is the same characteristics that we see previously, that we see before in the other videos. So it's very rare, and people recorded these videos, they put at the social media, YouTube, things like this. And we analyzed these videos trying to understand what is happening. So this recording is the exactly time that the things happened, and you see here this abrupt change. The dimensions are very huge, of the dimensions of this phenomena, if you imagine the size of the cloud. central question or scientific question. How does the collective orientation of ice crystal under electric fields and temperature variation generate this dynamic and discontinuous optical pattern? So we have here our approach. Basically, first we analyzed real videos of the phenomenon. Second, we use ferrofluids as a laboratory analog. They form similar light patterns under a magnetic field. Third, we modeled this system using dynamical systems and Ising model. In our experiment, you use the ferrocell. There's a thin film of ferrofluid between two glasses. It behaves as a magnetic lens, and this is a handhelder with this lens here. You have the source of light here. You put a magnet, and you see patterns. This pattern created by the magnet. Basically, this is the main idea of using ferrocell. Well, in ferrofluids, magnetic needles align with the field. Light scatters perpendicular to them, forming plumes identical to the atmospheric phenomenon. This suggests that ice crystals act as electrical dipoles in an analogous way. So here you see this shape of plume, and this is the magnet, and this jumping sundog, and here you have the plume formed with the ferrofluid and magnetic field, and image of a sundog changing the shape, and here we are able to change the shape of the light pattern with the ferrofluid too. Well, we have here physical analogy, or in this table you have the analogy in this way. Just as magnetic needles align with magnetic field, ice crystals with an electric dipole moment align with the cloud's electric field, and they may undergo a phase transition with the temperature. So here is the ice crystals, hexagonal columns of ice crystals, and the shape of the jumping sundogs, and here you have the magnetic micro needles in the ferrofluid, and here we can change, aligning them with a magnetic field. So if you put an external magnetic field, you can orientate this magnet here in one direction or another direction. These magnets will scatter the light, will reflect the light, so you have this luminous pattern obtained that we observe in these videos. Here you can see a magnetic field controlling light in our laboratory. We are changing the position of the magnetic field, and in this way we have the light scattered by the ferrofluid changing the position of this magnetic jumping sundog. uh, we have first this model, or for a single crystal, we modeled a, a system using this circle map, this 2D circle map. This is a simple system that generates oscillations and chaos. The resulting time series reproduce the Plume oscillations, and the attractor from our model looks like a rhino horn. This is a chaotic attractor, this that we call rhino horn, and this is the position, the angular position of the jumping sundog recorded in the video, and we did this plot. And this is our model using dynamical system, as the system is working as just one solid body, oscillating, and it can be modeled by this 2D circle map. But now we are proposing a collective behavior. In this system here, we are imagining that for many crystals, we use the 2D Ising model, 2D Ising model. Below the critical temperature, spins align in one direction, then crystals are oriented. Above it, orientation of the spins are random. The figures show the characteristic cluster formation at this transition. So here you have below the temperature, you see in this 2D Ising model that you see this pattern, and above the critical temperature you have this other pattern, and for at the critical temperature you have these distributions of spins, and the orientation of the spins is related to our orientation of ice crystals, or orientation of the magnetic needles. Well, we have here, if we consider now this new model, not the model of a two-dimensional circle map, but now we are imagining the statistical phenomena. Below the critical temperature, the system is bistable. It can fall into either of two potential wells, as you can see here, and which one it chooses depends on its history. That is a memory effect which is unusual in atmospheric optics. So we are proposing the idea that this phenomenon has a kind of memory. If the ice crystals, the systems coming from here, it remains here and jumps to this direction, and if it's coming from here, it jumps in this direction. So you have two states, one state that's stable here, another state that's stable here. So this is the memory effect, that you have this state or this state. If the system is coming from here, from this part, it moves in this direction, and suddenly it jumps. It in magnetism, it's called the Barkhausen jump. So in our model, or using statistical mechanics, we are proposing that the jumping sundogs are related with Barkhausen jump. Let me show you here spinning magnets. So here you see it is one state. Now let me disturb the central part of these systems, and you see another state. We we disturbed the system here, and let me show you again these simulations with these magnets, with these spinning magnets. The idea here is that you don't need a strong external magnetic field. The system itself creates these orientations. So we have hysteresis and Barkhouse jumps. When we vary the electric field, the system can jump from one stable branch to another. These Barkhouse jumps explain the whip-like motion. A small change in the cloud triggers an explosive sudden reorientation of the crystal. So you are in branch 1, you are in this state, and you jump to this branch 2 and this 2 second branch in the first one case. What is the whip-like motion in ferrofluid? In ferrofluid, we can see this whip-like motion when we have this light pattern that's closed, changing a little bit the magnetic field. The system opens, so we have this whip-like motion when you transition to 1 to 4. This is a video of this closed figure, and when it opens, when they open, let me show you again here. Here you see this is the whip-like motion. Criticality, no external field. It's possible to have this system without external field, just the polarization of the ice crystals in the cloud. It's not necessarily a giant external electric field surrounding. It's just the motion is related just with the polarization of the ice crystals inside this cloud. This is a fascinating alternative hypothesis, is that jumping sundogs may be a purely critical phenomenon. The external fluctuations near the cloud's critical point could be strong enough to reorient the crystals without any external electric field, just like critical opalescence is analogy to what happens in critical opalescence in supercritical fluids in this situation, in this condition of the critical temperature. In summary, our unified mechanism is this: crystals behave as electric dipoles. Below the critical temperature, they are in an ordered ferroelectric state. Then small fluctuations or discharges in the cloud's electric field cause abrupt Barkhouse jumps, which we see as the whip-like motion. And crucially, the system has a memory of its previous state. So this is the idea that causes the jumps in the sundog. Why it's rare? It's very difficult to observe this. So it's very difficult to predict. In our opinion, with our model, we consider that the rarity of jumping sundogs is explained by this specific combination of conditions. The right hexagonal crystal shape, you have to have this crystal shapes in ice crystals in the shape of columns, a temperature right at the critical point. It will not happen at all temperatures, but to very specific thermodynamic conditions for maybe temperature, maybe pressure, you have a strong but non-destructive electric field. And finally, the observer being in the perfect position to see it. If it's not observing in the right position, you cannot see what is happening. But this is the main idea of our work, that these conditions must be satisfied in order to observe the jumping sundogs. Conclusions. We conclude that jumping sundogs are a rare, critical phenomenon with memory, modelable by dynamical systems and statistical mechanics. Ferrofluids provide a powerful experimental analog. Open questions remain, we cannot avoid, such as how to measure this critical temperature, these critical thermodynamical conditions in real clouds, or if we can observe the hysteresis directly. These are some videos that we used to do this work. You can see here some of previous papers working with the system. And these are the open questions: how we can measure the critical temperature in situ inside a real cloud. Is the predicted hysteresis directly observable in high-speed videos? Can we develop a full 3D model with many interactive crystals? I guess that's possible, because I already seen something similar in ferrofluids, in a tank of ferrofluids and magnets, and you can see something very similar to this motion of the jumping sundogs. Thank you. We are open for questions. You can put your questions in the comments. Thank you.